In this lesson, we're going to solve systems of equations using matrices. Before you do this lesson, you should have already solved systems of equations by the graphing technique, by substitution, and by elimination. You might recall that as the number of equations gets larger and we have more variables, the more difficult those types of solutions become. It becomes rather difficult to keep organized and stay up to date on what you've done with each equation when you use either substitution or elimination. Before we look at solving an actual system of equations, we want to spend a little bit of time talking about matrices and how matrices can represent systems of equations. So let's take a look at what we mean first of all by a matrix. A matrix is a rectangular array of real numbers. The rows run horizontally and the columns run vertically. I've shown here on the screen an example of a matrix that has 2 rows and 5 columns. Notice going horizontally there are 2 rows, and then going vertically 1, 2, 3, 4, 5 columns. Now I help to remember this by thinking about columns on a home or up and down vertical like that, and so that helps me to remember that the columns are vertical in a matrix. You'll notice this sort of rectangular shape here. We usually use a bracket to enclose our matrix just to indicate that we do have a matrix, and then you'll notice I just have numbers put here in these rows, or I can think of the numbers being listed in columns within this matrix. Now sometimes if you study matrices in a little bit more detail, you'll find that we talk about particular terms in the matrix, and we can give that by location. For instance, this 1 right here is in the first row and it's in the 3rd column. So that 1 is in the first row, 3rd column. And we can designate other entries in the matrix by doing those sorts of things. In this lesson, we're not going to spend a lot of time dealing with matrices themselves, but we want to see how we can use a matrix to represent a system of equations. Now, there's one other thing, though, about matrices that I want us to look at before we look at the systems of equations. If we have what's called a square matrix, by a square matrix we just simply mean that we have the same number of rows as we do columns. And so if you notice across here I've got 1, 2, 3, 4, 5, 6, 7, 8 columns. Coming down 1, 2, 3, 4, 5, 6, 7, 8 rows. There's 8 rows, 8 columns, which makes this nice and square. And if you can see these letters that I've written in here, D-I-A-G-O-N-A-L, that stands for diagonal. So when we talk about the diagonal of a square matrix, we're talking about these entries along this diagonal here. Now you'll notice this is first row, first column, second row, second column, third row, third column, fourth row, fourth column, and so on. When we do our systems of equations, we're going to be referring to this diagonal here, and so I wanted you to be sure and see what we mean by the diagonal of this square matrix. Now, in our next definition, we're going to look at what we mean by an augmented matrix. Now don't get too worried about that word augmented. When you augment something, you add to sort of that idea. But let's look at what we have here. The system of equations, 3x minus 2y plus 5z equals 7, 8x minus 4z equals 9, x plus y minus 2z equals negative 6, can be represented by the matrix given here. Now I want us to examine this matrix. In particular, let's look at this first row. Notice that in this first row I have listed the coefficients of my variables, and then this 7 is the constant that my equation is equal to. Now it's very important, if you're going to represent a system of equations in a matrix form, that first of all you write the equation in this type of a format where you've got your variables all over here on the left hand side of your equation and your constant term is over here on the right. You'll also want to be sure that each equation in your system has the variables in the same order. Notice we have x first, y is second, and you'll notice y does not appear in that second equation, and then we have z. Each row in this matrix represents one of our equations. Notice that the first column of this matrix are the coefficients of x, 3, 8, and 1. The second column are the coefficients of y, 2. Notice I have a 0 here because there's not a y in this second equation, so I have a 0 here, and then my 1. The third column are the z values, 5, -4, and -2. And then this last column of my matrix are these constants that my equation was equal to. In some textbooks, when they write this augmented matrix, sometimes they will put a little dotted line right through here. That dotted line separates the coefficients of your variables from the constants. Sometimes this part of the matrix is referred to as the coefficient matrix. And then this column over here, of course, is your constants. You'll notice here, this coefficient part of the matrix is a square matrix. 3 columns, 3 rows. That will always be the case if you have the same number of equations as you have variables. Now, if I look at this part of my matrix, this square matrix right here, notice that the diagonal of that coefficient matrix is 3, 0, -2. Okay? So we're looking at this diagonal right here. We'll talk more about why we care about that diagonal a little bit later. So the idea of representing a system of equations in matrix form is that each column in my matrix will represent coefficients of variables, and then finally the constants. Each row in the matrix represents an equation. You'll notice what we're not writing are the variables and the equal sign. Okay? Having looked at this sort of definition, if you will, for augmented matrices, this first problem wants us to write the augmented matrix for the given system of equations. Well, the first thing I'm going to notice is that each equation has all the variables on the left and the constants on the right, and also that my variables are in the same order over here. You'll notice in my middle equation I don't have an x variable, but otherwise the variables are in the same order. So to write my augmented matrix, I'm going to make a bracket. In the first row of my matrix, I'm going to list my coefficients and my constant. The coefficient of x is a 1. The coefficient of y is a 2. The coefficient of z is -1. And my constant is a 1. Now you'll notice that if the coefficient is positive or if the constant is positive, I do not have to write that plus sign. But if I have a negative coefficient or constant, I will need to write the negative in my augmented matrix. Okay, let's go to the second row now of our matrix, and let's write the coefficients. Notice this first column is for x. Since I do not have an x, I'll put a 0. I have a +2 in front of y, a 3 in front of z, and a 5 for my constant. And then finally, in the third row, my third equation, I have a 3 in front of x, -2 in front of y, 1 in front of z, and my constant is 0. Now, you may leave your augmented matrix just like this, or if you prefer, like I mentioned in the last little problem, you could put a dotted line here that separates the coefficients from the constants. Now, sometimes the dotted line is a good idea because it does sort of help you separate things, but also be careful that you don't get these dots in here where you think you've got a number in front of that 5, like looking at that as a 15, if you get a big dash right in front of that. So just be careful if you choose to use that dotted line that you're very careful. So you can see in this example it's very easy to take a system of equations and write it into this augmented matrix form. Now, in this next example, we're going to do something a little bit different. Notice here he says to write the system of equations represented by the matrix. So here we have the given matrix, but we want to know what system of equations might that represent. Since I have two rows in my matrix, I know I will have two equations. Now remember, the first columns are the coefficients of my variables. The very last column would be my constants that the equations are equal to. So because of that, I can see that I will have two variables and then constants. You may choose whatever variables you want to use. Of course, generally we like to use x and y. So what I'm going to do is just make a note here that this first column is going to be the variable x, the second column is going to be the variable y, and then these will be my constants. So my first equation would be 4 times the variable x minus 3 times the variable y, and then equals the constant 7. My second equation would be 1 times x, of course we usually just write x for that, plus 2 times y equals negative 3. So this is the system of equations from this augmented matrix. This also says to write the system of equations represented by the matrix. So again, I've got two rows, so there's two equations. This might be first column for x, second column for y, and then my constants. Let's write these equations. I have 1x plus 5y equals 2. And notice in this second equation, my coefficient of x is a 0. So I don't even need to write 0x. 0x is just 0. So I'm just going to have 1 times y equals negative 4. Now I want you to notice something about this system of equations that I've written. Notice this second equation is solved for y. I already know what the value of y is. Since I know y, I could do what we call a back substitution. Go up to this equation and substitute y in. If I do that, I have x. If y is negative 4, 5 times negative 4 would be negative 20. This is equal 2. And then notice that allows me to solve for x by adding 20 to both sides. So I have a solution. X is 22 and y is negative 4. Now, the reason that I wanted you to look at this example is to notice that if my coefficient matrix, let me put a dotted line in here to separate that. Notice on my coefficient matrix, what do I have on the diagonals of that coefficient matrix? I have 1s. Notice that I'm going to call this below that diagonal. Below my diagonal over here, I have a 0. That's what caused this second equation to be y equals negative 4. And notice then I could go back up to the equation represented here and substitute in. This form of the coefficient matrix is sometimes called a triangular matrix. That's because, notice if I take that diagonal, that part right there, it sort of forms a triangle. A triangular matrix has zeros over here in this other part, so that we just have numbers in this upper triangular part here. If we could get a matrix that represents a system of equations into this triangular form, then notice how easy it is to solve that system. Okay, well here's another problem that we are to write the system of equations represented by the matrix. Notice here I've got 3 equations, and again, if you want to separate that last column for the constants, how many variables do you have? You have 3 variables. Let's call the first variable x, the second one y, and the third one z. Now let's write this first equation. I have 1x minus 2y minus z is equal to 4. Let's look at the second equation. Notice my coefficient of x is 0. So I have 1 times y plus 3 times z equals negative 1. And then look at your third equation. X and y both have coefficients of 0. So I have 1z equals 2. Well, notice again on this coefficient matrix, do you see that nice diagonal right there on my coefficient matrix? Look at all those ones on that diagonal. What's down here? All zeros. So I have this coefficient matrix again in that nice triangular form. And look what happens over here. I know Z. Look, if I substitute back up here, I can find Y, can't I? Y equals, if Z is 2, 3 times 2, I'm sorry, Y plus, said that wrong, Y plus. If Z is 2, 3 times 2 is a 6, equals negative 1. And then subtracting 6, I get Y equals negative 7. Now I know both Z and Y, and so I can go back up to this first equation and substitute in. I have X, negative 2 times Y. Well, if Y is negative 7, negative 2 times negative 7 is a positive 14. And then minus Z, well, if Z is 2, minus Z would be minus 2, equals 4. Well, let's see, that's X plus 12 is equal to 4. And then subtracting my 12, I get X equals negative 8. So X is negative 8, Y is negative 7, and Z is 2. So again, if my equation, or my matrix that represented my equations was in this nice triangular form for the coefficient part, then I got this nice system of equations which allowed me to back substitute and find my values of X, Y, and Z. Okay? Well, here's another one that says to write the system of equations represented by this matrix. Again, I have how many equations? 3. Here's my constants, so how many variables? 1, 2, 3 variables. Let's let our first variable be X, then Y, and then Z. Now let's look at our first equation. I have 1x. Notice I have 0 y's and 0 z's equals 4. Look at the second row. 0 x's, 1 y, 0 z's equals negative 1. And my third equation, I have 0x, 0 y, 1 z equals 5. Well, look, I have my solution right here. 4, negative 1, 5. I didn't even have to do any back substitution. Well, let's examine the coefficient part of this matrix. Look at the diagonal of that coefficient part. Look at all those ones. But notice on this one, besides the diagonal, everything else is zeros. And because of that, we got this nice system of equations over here that basically was our solution to the equation. It was our answers. So what we're seeing here is if we have a system of equations represented in a matrix form, if I can get the coefficient part of that matrix either in this triangular form like we saw in this example, or in this form where we have ones on the diagonal and zeros everywhere else, then it's a pretty easy matter, here extremely easy, and here not too difficult, to find the exact solutions of our system of equations. Now what you're seeing here is that we know what we want to get that augmented matrix to look like, so the question is, how do we do that? How do we get the coefficient part of that matrix to either be in triangular form or to have the ones on the diagonal and zeros everywhere else? Well, as it turns out, we can do that by using what we call elementary row operations. There are 3 elementary row operations that you are allowed to use when you're working with a matrix that represents a system of equations. Let's take a look at what those are. Elementary row operations. Notice the first operation is to interchange 2 rows of the matrix. Interchange 2 rows of the matrix. The second one is to multiply a row by a non-zero real number. And the third one is to add a multiple of a row to another row. Now let's examine these row operations and talk about exactly what that might mean for us. To talk about that, I want to go back to this problem that we had earlier that said write the augmented matrix for this system of equations. Now this is the matrix that we wrote. What if I take this matrix and I interchange two rows? That means just switch the position. What if I write the first row where the second row was and write the second row up here where the first row was? I'm going to leave the third row just like it was. If you look at this, what effect does this have basically? All I've really done is to take these two equations and write them in a different order. See, each row in the matrix represents an equation. Does it matter what order your equations are listed in? It doesn't, does it? So if I interchange the order of these equations, that's equivalent to just interchanging the rows of your matrix. So that's why we can do that first row operation of interchanging two rows of the matrix. We're just changing the order that our equations are written in. Now, the second operation said we could multiply a row by a non-zero real number. Now, let me go back to this original form right here. What if I decide that I'm going to leave the first row just like it is, but I'm going to multiply the second row by 2. Now that means every number here in this second row. Well, 2 times 0 is still 0. 2 times 2 is 4. 2 times 3 is 6. And 2 times 5 is 10. I'm leaving the other rows in the matrix totally unchanged. What did I really do right here? Well, notice this equation right here. If I have 2y plus 3z equals 5, is it okay for me to multiply both sides of that equation by the same number? It is, isn't it? We've always been able to do that. Notice if I multiply both sides by 2, I get 4y plus 6z equals 10. Now look at this row right here. 0x 4y plus 6z equals 10. So this second row operation of simply multiplying a row by a non-zero real number is just like multiplying both sides of an equation by the same number. Now you'll notice I said non-zero. We can't multiply both sides by 0 because that would just wipe out the equation, wouldn't it? So that means we can't multiply a row by 0 either. Now, this last operation is the more complicated one. It says to add a multiple of a row to another row. Add a multiple of a row to another row. Now, to do that one, I'm going to get a clean sheet of paper here, and I'm going to recopy the matrix that we had. Again, I'm going to use this same system of equations that we started with. 1, 2, that was -1 and 1. The second one we had a 0, 2, 3, and 5. And the third one was 3, -2, 1, and 0. Now, I want to go ahead and write these equations again over here also. X plus 2y minus z equals 1. Let's see, 2y plus 3z equals 5. And 3x minus 2y plus z equals 0. Now, let's talk about just in the equation format for a second. If I look at this system of equations, one of the things that we talked about doing sometimes was choosing two of the equations and deciding to eliminate a variable, didn't we? Well, let's look. If I take these two equations right here, I can eliminate x if I multiply this first equation by -3 and add the results to this second or this third equation, right? If I multiply this top equation on both sides by -3, I get a -3x, -6y, plus 3z equals -3. Now, if I add these two equations, notice the x's are eliminated. I get a -8y plus 4z equals negative 3. Now, what I can do then is I'm going to keep this equation and I'm going to keep this equation, but I'm going to replace this third equation with this new equation that I've created here. Okay? And that's basically the same sort of thing that you do when you do the elimination method. Now, let's translate that over here to a matrix and see how that compares over here. If I take this first row and multiply it by negative 3, and I'm going to put the answers down here. Negative 3 times 1 is negative 3. Negative 3 times 2 is negative 6. Negative 3 times negative 1 is positive 3. And negative 3 times 1 is negative 3. Now, if I leave the first row of my matrix the same, I leave the second row of the matrix the same, but then I add these. What am I doing? I'm adding a multiple of this row to the third row. I get 0, negative 8, 4, and negative 3. Notice that third row now represents this new equation where I've eliminated x using two of my equations. And if you notice what it's done, it's created a 0 here. So I'm sort of on my way now to having what I want here and having zeros down here. So let's look at that third row operation again. We can add a multiple of a row to another row. Now, the thing that's important on this one is you're going to take a multiple of a row. That row actually itself does not change, but you add those numbers to this other row, and that's the one that changes. We'll try to work on that as we do some of these row operations. Now, I have here symbols for row operations. Now, every textbook will be just a little bit different, so your textbook may show you something a little different than these operation symbols, but most of them are fairly common. This first one, this little double arrow, is indicating to interchange. This is saying row number 2 is interchanged or changes places with row number 3. Okay? This says I'm going to multiply 1/5 times row number 4. And this arrow says it replaces or it becomes the new row 4. Now most books will not write that word new in there, but we're trying to emphasize we're changing row 4 by multiplying all the numbers in row 4 by 1/5. And that creates a new row 4. It's just like multiplying both sides of an equation by 1/5, remember. This last one says we're going to take 3 times row number 1 and add it to row number 2, and you'll notice that becomes the new row number 2. Notice the row we're adding to is the one that's replaced. The multiple of row 1 is just being used to change row 2. Row 1 itself does not change. Now, as we work on these row operations, we're going to try to use these symbols because that tells us what it is we're trying to accomplish. And I assure you, when your instructor grades assignments on this, they're going to want to know what were you trying to do, because sometimes you make careless mistakes and it's difficult to tell exactly what maybe you were trying to do. Now, let's see about using these symbols, and we're going to just do a few simple row operations. This is telling us to change the matrix by interchanging rows 1 and 3. Now what I'm going to do is just draw an arrow. Now I don't put an equal sign because these matrices are not equal. We're changing the matrix, notice. We're going to change it by interchanging rows 1 and 3. So what I'm going to do is write row sub 1, and then I'm going to do that double arrow, row sub 3. Row 1 and 3 are going to change places. So I want to do my little matrix symbol here. Row 1 is going to come down here to the bottom where row 3 was. Notice row 2 is not moving anywhere, so row 2 is still right here. But row 3 is going to go up here and take the place of row number 1. So I have simply switched rows 1 and 3. Row 2 stayed the same. This is my symbol. Now I want you to look at what we've done and tell me what we've accomplished by interchanging these rows. Notice what I've accomplished is I have a 1 on that upper corner right there, And notice that upper corner is the first number in my little diagonal there, okay? So I'm going to point that out again as we start solving some systems of equations. We're going to want to get a 1 up there. So one way to get a 1 up there is if there's a 1 in that column somewhere, we can interchange the rows and put that 1 right up there where we want it. This one says to change the matrix by multiplying row 2 by negative 1/3. Okay, so we're going to draw an arrow, says we're going to change the matrix. I'm going to say negative 1/3 times row number 2. That's what I'm going to do. Notice this becomes my new row number 2. Let's look at what this said right here. 1/5 times row number 4 becomes my new row number 4. Now I did not write the word new. Sometimes I'll just put an N there for new row 2. The important thing is that you understand we're going to change row 2 by multiplying it by negative 1/3. Okay? So I'm changing row 2. Row 1 does not change. I'm going to leave it 147. Row 3 does not change. It stays 0, 1, negative 9. The only row that's changing is row number 2. Now, if I multiply negative 1/3 times 0, I still have 0. Negative 1/3 times negative 3, notice, gives me a positive 1. Negative 1/3 times 2 gives me negative 2/3. Okay? So I've changed my matrix by multiplying negative 1/3 times row number 2, and that became my new row number 2. Now, what did I accomplish by doing that? Well, look along this diagonal right here, guys. I've got my 1 here, and now I've got a 1 here. I've got a couple of zeros. I don't have a 0 here yet, but do you see I'm on my way to getting this matrix sort of in that triangular format, okay? Well, let's do one other row operation here. It says to change the matrix by adding negative 2 times row 1 to row number 2. Okay, well, let's draw our arrow here. We're going to take negative 2 times row 1, so let's write that, negative 2 times row 1. We're going to add that to row number 2, and that becomes my new row number 2. Remember, the row you're adding to is the one that changes. We're adding to row 2, that becomes the new row 2. This multiple is just being used to change that row. Now I want to emphasize, this is the one you have to be careful about. We're changing row 2. We are not changing row 1. So what I want you to do is let's just recopy row 1 over here so you won't be tempted to change it. We're not changing row 3, so let's recopy row 3. We're changing row 2. How are we going to change row 2? We're going to take negative 2 times row 1 and add those numbers to row 2. Well, let's look right here. If I multiply the numbers in row 1 by negative 2, let's think about what we get. I'm just going to write them down. I hope you can see them on the screen. Negative 2 times 1 is a negative 2. I'm just going to write that underneath that 2 right there. Negative 2 times 5 is negative 10. Negative 2 times negative 3 is a positive 6. Now I wrote those right by these numbers in row 2 because I'm going to add those to those numbers. 2 and negative 2 added together gives me 0. Negative 1 and negative 10 added together gives me negative 11. 0 and 6 added together gives me 6. Now, I encourage you to make room on your paper to write down these numbers that you get when you do this multiplication so that your eyes are looking at those numbers and you don't make a careless mistake right here. If you make a careless mistake right here and get the wrong numbers on this row, then from there on you're going to have incorrect solutions for your system of equations. It's very important to be accurate with this. So don't try to do everything mentally or you may make a careless sign error here. Now that we have looked at all of the row operations, we're ready to talk about how do we use these row operations to change a matrix that represents a system of equations into a nice matrix where it's easy for us to get the solutions to that system of equations. Now there's really two sort of techniques that we're going to look at. They're basically the same procedures, except that one technique just goes a little bit farther than the other. One of these techniques is referred to as Gaussian elimination. That's named after a famous mathematician, Gauss. The other process also uses Gauss's name, but it also involves another mathematician because they work together. It's referred to as Gauss-Jordan elimination, and there's just a slight difference between the two. We're going to look first of all at Gaussian elimination, and then we'll do a few examples, and then we'll talk about Gauss-Jordan elimination and see what that does for us. Elimination is the process by which elementary row operations are used to put the coefficient part of the augmented matrix in triangular form. So what we're looking for here is to use the three row operations that we've talked about that will put our matrix in a triangular form. Recall the triangular form was the one that we looked at like this, where we have ones on the diagonal of our coefficient part of the matrix. We have zeros down here below. And in that triangular form, then notice that we had this last equation that is already solved, and then we can back substitute to find the other values. So that's what we're after. Notice we're going to want to get a 1 up here in this upper corner. Diagonal down, we want ones, we want zeros below here. The only way that we can change the matrix is to use these elementary row operations. That's the only legal thing that we can do, and it's because those row operations mimic things that we're allowed to do when we work with equations. Now, we're going to start with a small system here just to get our feet wet, so to speak, and get involved in this process. It says to solve the following using the Gaussian elimination. So the first step here, we're going to write the matrix that is represented by these equations. So I have 2x, I have a minus 5z equals 1, and then I have a 3x minus 4y equals 2z. Okay? So there's my matrix. Now remember, this part right here is the coefficient part. So my objective is to get a 1 where the 2 and the negative 4 is, and to get a 0 where the 3 is. Now in general, to get a 1, you're going to use one of the first two row operations. The first operation said we could interchange the rows of our matrix. Well, notice, even if we interchange here, I would put a 3 up here instead of a 1. So interchanging the rows of the matrix here is not going to help. The other way that we can produce a 1 is to use a multiple of a row. In other words, multiply that row by some non-zero number. So what I'm going to do here, I know that I can change a 2 into a 1 if I multiply it by 1/2. So I'm going to multiply 1/2 times row number 1, and that's going to become my new row number 1. So notice here we're changing only row 1. Okay, so if I multiply 1/2 times 2, I get a 1. 1/2 times negative 5 gives me negative 5/2. 1/2 times 1 is 1/2. I'm just going to recopy these numbers in my second row. But notice what I've accomplished. I have a 1 in this upper corner. Now in general, the next thing you're going to want to do after you get your 1 in this upper corner is to try to get the 0 below that. Now the way to get the zeros is with that third row operation, where we take a multiple of one row and add it to this row that we're going to change. Now since I have a 1 up here, If I multiply 1 times negative 3, I'll get a negative 3. And if I add negative 3 to positive 3, I will get a 0. So what we want to do is multiply negative 3 times row number 1, add that to row number 2, and that's going to give me my new row number 2. This is the one that I cautioned you about. Which row are we changing? We're changing row 2. So before we do anything else, we're going to recopy row number 1. Row number 1 is not changing here. But we're going to use this row to change this one. So multiplying 1 times negative 3, we get a negative 3. I'm going to write that right underneath right here. If I multiply negative 5 halves times negative 3, I'm going to get a positive 15 halves. Now this is going to give your arithmetic a good workout, particularly fractions sometimes. If I multiply 1 half times negative 3, I get a negative 3 halves. And you may want to use scratch paper to help you out sometimes. Okay, notice if I add 3 and negative 3, I get 0. Now, I'm going to suggest that we use a little bit of scratch paper right here. Notice here I've got negative 4 and I'm adding 15 halves. Well, let's put that over 1. My common denominator is 2, so I have negative 8 halves plus 15 halves. That gives me 7 halves, doesn't it? So my number right down here is 7 halves. And then I need to add these two. So again, with my scratch paper, I have a 2 minus 3 halves. Put 2 over 1. That's 4 halves minus 3 halves gives me 1 half. Now, it's very important to be careful with your arithmetic. I can't stress that enough. If we miss these numbers, the solutions to our equations are not going to be correct. Now, let's take a glance at where we are. I've got a 1 in the upper corner. I've got a 0 underneath it. Now, I want to diagonal down, and I want to change this number here into 1. Remember, we want 1s on the diagonal. Now, remember, to get 1s, we either interchange or we use a multiple of that row. Now, interchanging, again, would only mess up what I've done so far. So what I want to do, what do I need to multiply times 7 halves to give me a 1? It needs to be the reciprocal of 7 halves, doesn't it? So I need to multiply 2 sevenths times row number 2. That becomes my new row number 2. So again, row 1 is not changing. 1, negative 5 halves, 1 half. If I multiply 2 sevenths times 0, I get 0. 2 sevenths times 7 halves is 1. And 2 sevenths times 1 half is going to be 1 seventh. If you need to go to scratch paper, do you see your 2's are going to cancel? 1 seventh. Now, look at the coefficient part. I've got 1's on the diagonal and a 0 underneath, so I've got it in that triangular form. Notice this last row, the equation x, 0x plus 1y equals 1 seventh. We have our y value. The first row is saying 1x minus 5 halves times y equals 1 half. Okay? Now, since y is a 1 seventh, let's substitute that in. 5 halves times 1 seventh is going to be 5 fourteenths. Since I got fourteenths here, I'm going to change 1 half to 7 fourteenths. And then to solve for x, we will add the 5 fourteenths over here and get 12 fourteenths, which will reduce to 6 sevenths. So x is 6 sevenths, y is 1 seventh. So the procedure was, after we wrote the matrix that represent our system of equations, we wanted to get a 1 in the upper corner, then we wanted to get a 0 underneath it, diagonal down, get a 1 here, and then since this one at this point was finished, we had it triangularized, then we have our system of equations that we can just get the answer and back substitute. Now you might be saying, this seems harder than just taking this and doing elimination like we learned. Well, you're right, it is. And usually on two variables and two equations, I would do elimination. But what we're trying to show you here is a very systematic technique, and this technique is very good to use when you have very large systems of equations, where you have 4 or 5 equations and 4 or 5 variables, because that way we keep everything organized. If you remember elimination, even with 3 variables, sometimes you get confused a little bit. If you go to 4 variables, it is difficult to keep up with what all you're doing to get the solution. The other thing about this process is that because of the systematic way that we can go about getting these ones and zeros, it's a very nice method that we can program for a computer to do. And so once we understand the process, we could ask a computer to do all of this hard arithmetic for us, and then it would be very easy to read off from the final results of the computer what the solutions to the system would be. Now, let's do one more of these where we're doing this Gaussian elimination. This time we're going to do one that has 3 equations and 3 variables. Okay, well, let's start by writing the matrix. So I have 2x, 1y, minus 3z equals negative 11, 1x minus 2y plus 1z equals negative 3, 1x minus 3y plus 4z equals 6. Be very careful that you're sure you write down those coefficients exactly correct, because again, if you make a mistake right there, everything from there down would be wrong. Now, here we want to get a 1, zeros underneath, diagonal down, get a 1 here, 0 underneath, diagonal down and get a 1 here. So we want 1s along here, zeros here. Now, the first objective is to get a 1 in this upper corner. Now, this time it would be very easy to interchange equations and get a 1. I can interchange the first one with either of the second one or the third one. It really isn't going to matter. So I think what I'm going to do is I'm going to interchange row 1 and row 2. Okay? So let's see. If I put row 2 first, I've got 1, negative 2, 1 and negative 3, and then I'm going to write row 1 down here in the second position, 2, 1, negative 3, negative 11, and we will recopy that third row. Okay? So we've gotten our 1 up here in this upper corner. Now, after I get my 1 in the upper corner, I want to get zeros down underneath here. Now, sometimes I will combine this and do 2 steps sort of together. I'm going to put my arrow over here because I don't have room. I'm going to change row number 2 first of all. If I multiply 1 times negative 2 and add to 2, I'm going to get a 0 here. So I want to multiply negative 2 times row 1, add that to row 2, and that will become my new row number 2. Okay? Now, let me draw my matrix. I'm only using row 1 to change row 2. So I want to recopy row 1 before I do something crazy and change that. And you'll need to learn to do that also. Now, notice that to change row 2, we're going to use negative 2 times row 1. So let's look right here. If I multiply negative 2 times 1, I get a negative 2. If I multiply negative 2 times negative 2, I get a positive 4. If I multiply negative 2 times 1, I get a negative 2. And if I multiply negative 2 times negative 3, I get a positive 6. Now let's add those numbers. I get a 0. 1 plus 4 is 5. Negative 3 minus 2 is negative 5. And negative 11 plus 6 is negative 5. Okay? Now while I'm here, since I got the 0 here, I'm also going to get the 0 down here. So I'm going to change also row 3. Notice if I use row 1 again, all I have to do is to multiply row 1 by negative 1 and add to this. So negative 1 times row 1, or minus row 1, added to row 3 is going to become my new row number 3. Okay, so I'm going to multiply negative 1 times row 1. That give me a negative 1. Negative 1 times negative 2 is a positive 2. Negative 1 times 1 is a negative 1. Negative 1 times negative 3 is a positive 3. Now let's add those numbers. I get another 0. Negative 3 plus 2 is negative 1. 4 minus 1 is 3. And 6 plus 3 is 9. Now, I've combined two steps in one, and I like to do that because I know you get tired of recopying this matrix a bunch of times, and so do I. If you get having trouble with that, you may want to only do one of these at a time. Now, let's see where we are. We have the 1 up here in the upper corner, and I've got zeros underneath it. So now I want to diagonal down to this 5 right here, and I want to change that 5 into a 1. Now, there's two ways I could get there. I could interchange these rows, and then I could just multiply by a negative to change that, and that would get me a 1. Or I can multiply this row by 1/5. Well, I think what I'm going to do is just go ahead and multiply this row by 1/5, because I noticed that that's going to divide evenly. I won't even get a fraction if I do that. So we're going to change row 2 by multiplying 1/5 times row 2. That's going to become my new row 2. Now I'm going to have to slip another sheet of paper up here to accomplish this. Now let's scoot over this way a little bit if you can see that. Notice we're changing row 2. So I'm going to recopy row 1. 1, negative 2, 1, negative 3. I'm going to multiply 1/5 times row 2, and that's going to become my new row 2. So 1/5 times 0 is 0. 1/5 times 5 is 1. 1/5 times negative 5 is negative 1. 1/5 times negative 5 is negative 1. And then I'm going to recopy this third row down here. Okay? Now, we're doing pretty good here. I've got my 1 and my zeros. I've diagonal down and I have my 1. Now I want to get a 0 underneath that 1. Well, we need to change row 3, don't we? Notice here, if I just add the numbers in row 2 to row 3, I'm going to get a 0 here, aren't I? So really what I'm doing is 1 times row 2 is going to be added to row 3, and that's going to become my new row 3. I'm not changing row 1, so let me recopy. I'm not changing row 2, so let's recopy. But we're going to add the numbers in row 2 to row 3. Now I can just look at those this time. 0 plus 0 is 0. If I add those two, I get 0. If I add those two, I get 2. And if I add those two, I get 8. Okay? Well, you can see we're doing really well here. 1 with zeros, diagonal down, 1 with a 0 under, diagonal down. I need to change that into a 1. Okay, well, how can I do that? Can't I do that by just multiplying 1/2 times row 3? And that will become my new row 3. Okay, let's do that and see. So I've got 1, negative 2, 1, negative 3. That row's not changing. Second row is not changing. If I multiply 1/2 times 0, I get 0. Again, 0. 1/2 times 2 is 1. And 1/2 times 8 is 4. Now you'll notice this coefficient matrix has my 1s and 0s underneath, so it's in triangular form. So this third row is saying x, y, z here equals 4. My second row, 0 x's, so I have 1y minus z equals negative 1. Let's go ahead and find y. If z is a 4, y minus 4 equals negative 1, so y equals 3. So I've got z and I've got y. Go to the first equation. X minus 2 times y plus z equals negative 3. Okay, I don't know x. Negative 2 times y is going to be a negative 6 plus z, so plus 4 equals negative 3. Simplifying, x minus 2 equals negative 3. So x equals negative 1. So my solution is negative 1 for x, 3 for y, and 4 for z. Once I got this triangular format here, here's my constants, then I could back substitute and solve my equation. Now what you've seen here is that it does take a little bit of time. You have to be careful with arithmetic, but the strategy is basically right there. Get a 1 in that upper left-hand corner, get zeros underneath the 1, diagonal down and get a 1, get zeros underneath that, diagonal down, get a 1. If there's something underneath that, get zeros. And do you see how you could just extend that to as many rows and columns as you had in your matrix? Now the only problem is that once I get that coefficient matrix in that triangular form, I still have to do some work in that back substituting to find my actual solutions. Now that process, getting that triangular form, is the Gaussian elimination. Okay? Now let's take a look at what we mean by Gauss-Jordan elimination. The Gauss-Jordan method. The Gauss-Jordan method is the process by which elementary row operations are used to put ones on the diagonal and zeros for all other entries of the coefficient part of the augmented matrix. So the difference here, notice that when we finished up just a moment ago in this Gaussian elimination, we had ones on the diagonal and zeros underneath it. But Gauss-Jordan says not only do you want zeros here, but you want zeros here. Recall that when we looked at an example early in this lesson, we had a matrix like this. If I had ones here and zeros everywhere else in that coefficient matrix, I got just straight off of that matrix what the solutions were. So this is easier to read off the solutions, but it's going to take just a little bit more work because we're going to have to get those zeros up there as well. Okay? Well, let's see if we can do a problem using this Gauss-Jordan method. Solve the following using Gauss-Jordan elimination. So let's start by writing the matrix. Okay, so I've got 1x minus 2y plus 1z equals my negative 2, 3x, 1y, 2z equals negative 2, negative 2x, 3y, negative 1z, and 0. Okay, so there's my matrix. Now, here we're going to get a 1 and zeros underneath, just like we did with Gaussian elimination. Now, this is nice. I already have a 1 right here, don't I? Okay? So, we're not going to need to do anything to change row 1 at this point. But I want to get zeros underneath here. And remember, we're going to kind of do this together in one step. So I'm not going to change row 1 at this point. So let me recopy row 1. I want to get a 0. Remember, to get a 0, you use a multiple of a row and add to this one. So because of my 1 here, I can multiply this by negative 3 and add to this and get a 0. So what we want to do is negative 3 times row 1. We're going to add that to row 2, and that will become my new row 2. Okay, well let's just do that while we're here. Negative 3 times 1 is negative 3. Negative 3 times negative 2 is positive 6. Negative 3 times 1 is negative 3. And negative 3 times a negative 2 is a positive 6. Now let's add the numbers. 3 and negative 3 added together is 0. 1 and 6 added together is 7. 2 and negative 3 added together is negative 1. And negative 2 added to 6 is 4. Okay? Now, I also would like to get a 0 down here. Use your 1 in the first row. What would you need to multiply this first row by so that when you add the numbers down here you get a 0? It would be a 2, wouldn't it? 2 times 1 is 2, added to negative 2 is a 0. So we're going to multiply 2 times row 1, add that to row 3, and that will become my new row number 3 now. Okay, well let's multiply the first row by 2. 2 times 1 is 2. 2 times negative 2 is negative 4. 2 times 1 is 2. 2 times negative 2 is negative 4. Now let's add. I get a 0. 3 and negative 4 gives me a negative 1. Negative 1 and 2 gives me a 1. And 0 and negative 4 gives me a negative 4. Notice that once I had the 1 in this upper corner, I used that 1 to produce my zeros underneath here, don't I? Okay? Now, I've got the first column all nice like I want it. So I need to angle down here, diagonal down. I want to get a 1 here. Well, notice I could get it by multiplying by 1/7, but if I multiply by 1/7, do you see the fractions I'm going to get? So I think I'm going to avoid that for a moment. Let's interchange rows 2 and 3. Do you see why I want to do that? Notice it won't mess up my zeros here, but it's going to put a negative 1 here, and then I can fix that negative real easy. So we are going to interchange rows 2 and 3. So let's recopy row 1. And I'll interchange. Let's put 0, negative 1, 1, negative 4. And 0, 7, negative 1, 4. Okay? Now I'm almost to a 1. What do I need to do now? I need to multiply that row by negative 1. So I'm going to do negative 1 times row 2. That's going to become my new row 2. Let me go to another sheet of paper here so we have plenty of room when we write that. So I'm going to recopy my first row. Multiply my second row by negative 1. Negative 1 times 0 is 0. Negative 1 times negative 1 is 1. Negative 1 times 1 is negative 1. Negative 1 times negative 4 is positive 4. And then I'm going to recopy my third row. Okay, so the nice thing about doing that interchanging of these rows is I avoided a fraction, at least so far. Okay, now I've got my 1 here and my zeros. I've got my 1 here. Now what I want to do is to get a 0 not only below my 1 but also above it. Okay, so let's talk about how we could get that 0 above it. Well, I'm going to use the 1 in this row right here. If I multiply 1 by 2 and add to negative 2, I'm going to get a 0. So I'm going to take 2 times row 2, add that to row 1, and that's going to become my new row number 1. Okay? I'm going to recopy row 2 right now. Notice I'm using row 2 to change row 1, but I'm not actually changing row 2. Okay, well let's say 2 times row 2. Well, 2 times 0 is a 0. I'm going to put it right up there. 2 times 1 is a 2. 2 times negative 1 is a negative 2, and 2 times 4 is 8. Now let's add those numbers. Notice the 0 added to 1 is still a 1. Because of my 0 here, that's not going to mess up my 1 that I had up there. That's very important. I don't want to go in circles. 2 and negative 2 added together gives me a 0. Negative 2 and 1 added together gives me a negative 1. 8 and negative 2 gives me a positive 6. Okay? Now, while I'm here, I also want to get a 0 down here. How will I accomplish that? 1 times what added to 7 will give me 0. I need to multiply that by negative 7, don't I? So negative 7 times row 2 is going to be added to row number 3. That's going to become my new row number 3. Okay, so we're multiplying negative 7 times row 2. Negative 7 times 0 is 0. Negative 7 times 1 is negative 7. Negative 7 times negative 1 is positive 7. Negative 7 times 4 is negative 28. Now let's add. I get a 0, 0, 6, and negative 24. Okay? Now let's take a look at where we are. I've got 1 and zeros under. Diagonal down, I've got 1. I've got zeros above and below, so we're going to diagonal down. I want to get a 1 right here. Well, notice here I don't want to interchange rows or that's going to mess these things up. So the way I'm going to get my 1 here is to multiply 1/6 times row number 3. That will become my new row number 3. So I'm not changing row 1. I'm not changing row 2. But I'm going to multiply 1/6 times this third row. 1/6 times my zeros are still zeros. 1/6 times 6 is 1. 1/6 times -24. Now if you need to, get you a piece of scratch paper. 1/6 times -24. Remember that -24 is over 1. Notice your 6 is going to cancel, so you get a -4. Okay? Okay. Well, we're getting really close here. We've got our 1s on our diagonal. We have zeros almost everywhere. We need zeros up here. Okay, so let's change row 1. How am I going to get a 0 here using the 1 down here in row 3? If I add this to this, I get a 0, don't I? So I'm going to just take row 3 and add it to row 1, and that's going to become my new row 1. Okay? Notice here, we are using row 3. We certainly don't want to change row 3 because it's exactly like we want it. But if I add the numbers in row 3 to row 1, I get a 1. 0 plus 0 is 0. 1 and -1 gives me a 0. 6 and -4 gives me a 2. Now while I'm here, I also want to get a 0 right there. So I can do row 2. Notice again, I just need to add, row 3 added to row number 2. It's going to give me my new row number 2. Okay, so if I add the numbers in row 3 to row 2, I get a 0, 1. 1 and -1 gives me a 0. 4 and -4 also gives me a 0. Now, we're finally finished, and let's look at this first row. X, 0y, 0z equals 2. So x equals 2. 0x plus 1y, 0z equals 0. So y equals 0. 0x, 0y, 1z equals -4. So here's my solutions. Notice they're straight off of that final form of my matrix. So the only difference basically between the Gaussian elimination and the Gauss-Jordan elimination is with Gauss-Jordan we keep finding zeros not only below the 1s but also above the 1s to completely reduce this coefficient matrix to this form right here. 1s on the diagonal, zeros everywhere else, and then we can just read off the solutions. Okay? Well, let's see. This says to solve the following using Gauss-Jordan elimination. Notice this system has 1, 2, 3, 4 variables, 1, 2, 3, 4 equations. Now, actually, we're beginning to get into some problems where this type of technique is the one that we really want to do because it's very difficult with this many equations to keep up with everything if we try to just do the old substitution or elimination process. Okay? Now, sometimes I save myself a little bit of work when I write down this first matrix. Let me scoot this up so we have plenty of room right here. This is going to need to be a big matrix. Remember, I want to have a 1 in this upper corner. Well, see, I can see that's not a 1. That's not a 1. That's not a 1. But this is. I'm just going to write this equation as my first row. That way I don't have to interchange later. So 1, -2, -1, -2, and then finally my constant -4. Notice this is x, y, z, and w, and then my constants. Now, other than wanting that equation written down first, these don't really matter. So I'm just going to go ahead now in order. I've got 2x minus 1y, 4z minus 1w equals 1. Then minus 1x, 1y minus 2z, 2w equals 5. 3x, 2y, 1z minus 1w equals 0. So here is my matrix that I would start with. And I've got a nice 1 right up here. Now, after you get your 1 here, remember we want to get zeros. All of these numbers down here. And so we're going to do all of this at once so that we don't have to rewrite this matrix a zillion times. So we're going to change this matrix. Let me make a big arrow here. I'm going to change row 2. I'm going to use the 1 up here to do it, to get my 0. What do I need to do? Don't I need to multiply this by -2 so when I add to 2 I get 0? Alright, so we're going to take -2 times row number 1, add that to row number 2, that will become my new row number 2. Okay? While I'm listing what all I'm going to do, how am I going to get a 0 down here? I just need to add the numbers in row 1. Okay, so I'm going to take just plain old row 1, add to row 3, and that will become my new row 3. And let's decide what we're going to do down here. Using the 1 up here, I need to multiply by -3 to get a 0, don't I? So I'm going to take -3 times row 1, add to row 4, and that will become my new row 4. Now you'll notice here I've just decided what all I need to do. Notice all I'm doing is using row number 1 to change all of those other rows underneath. So let me scoot this up and let's be very careful here that we don't mess up signs or anything. First thing I'm going to do is just recopy row 1. 1, -2, -1, -2, and -4. Be sure that you get signs and everything copied exactly the same. Now let's start with this. We're going to multiply -2 times row 1 and add those numbers to row 2. So here's row 2. If I multiply -2 times 1, I get a -2. -2 times -2 is a +4. -2 times -1 is a +2. -2 times -2 is a +4. And -2 times -4 is a +8. I like to write those numbers down so I can look at them. I get a 0. 4 and -1 gives me a 3. 4 and 2 gives me a 6. Remember, you're adding those. Don't let that look like 4 squared. -1 and 4 added together gives me 3. And 1 and 8 added together gives me 9. Okay? Now, to change row number 3, I'm just going to add the numbers in row 1. So let's just look at row 1 and 3 and add those. 1 and -1 added is 0. -2 and 1 added is -1. Adding -1 and -2, I get a -3. Adding -2 and 2, I get a 0. And adding -4 and 5, I get 1. So there's my new row number 3. Then one more here. I'm going to multiply -3 times row 1 and add those numbers to row 4. So looking at row 1, if I multiply by -3, I get a -3. -3 times -2 is +6. -3 times -1 is +3. -3 times -2 is +6. And -3 times -4 is +12. Now let's add those. I get a 0. 6 and 2 is 8. 1 and 3 is 4. -1 and 6 is 5. 0 and 12 is 12. Okay? So on that one step through, we used our 1 in our upper corner to get our zeros underneath. Okay? Now, let me slide this up and let's take a look. My next step is to diagonal down and make a 1 happen here. Okay? Now, I can multiply by 1/3, and I think I'm going to go ahead and do that because that will produce a 1. Notice by multiplying by 1/3, since these are all divisible by 3, I'm not going to get fractions, and it'll make those numbers smaller. So I'm going to change row number 2 here. I'm going to multiply 1/3 times row number 2. That's going to become my new row number 2. Okay? So row 1 is not going to change. Let's recopy. I'm going to multiply 1/3 times this second row. 1/3 times 0 is 0. 1/3 times 3 is 1. 1/3 times 6 is 2. 1/3 times 3 is 1. 1/3 times 9 is 3. And then I'm going to recopy this 3rd and 4th row. be careful that you recopy it exactly correct. Okay. Now let's take another look at this. I've got my 1 and zeros diagonal down. I've got my 1. Now I want to get zeros above and below. I'm going to use this 1 to get them. So again, we're going to do a lot of this all at once. To get a 0 up here, I need to multiply this 1 by 2 to add to that to get 0. So I'm going to multiply 2 times row 2, add that to row 1, and that will become my new row 1. Okay? Now let's look below. To get a 0 here, I just need to add those. So I'm going to add row 2 to row 3, and that will be my new row 3. And then I want to get a 0 down here in row 4. So I need to multiply this 1 by negative 8, don't I? Negative 8 times row 2 added to row 4 is going to become my new row number 4. So notice again, every time we're using row 2, so we're not changing row 2 at this point. So let's come on down here and let's recopy row 2 so we're not tempted to change it here. We don't want to mess up that 1. Okay, well let's start here. I'm going to multiply 2 times row 2 and add those numbers to row 1. So let's multiply by 2 and put the numbers up here. 2 times 0 is 0. 2 times 1 is 2. 2 times 2 is 4. 2 times 1 is 2. 2 times 3 is 6. Now let's add. 0 and 1 gives me 1. 2 and negative 2 is 0. 4 and negative 1 is 3. 2 and negative 2 is 0. 6 and negative 4 is 2. Okay? Now we're going to add row 2 to row 3 to become new row 3. So let's just look at rows 2 and 3 and let's add those numbers. I get 0. Notice 1 and negative 1 is 0. 2 and negative 3 is a negative 1. 1 and 0 is a 1. 3 and 1 is a 4. Okay? Alright. Then again, negative 8 times row 2. So let's look at row 2 and multiply by negative 8. Negative 8 times 0 is 0. Negative 8 times 1 is negative 8. Negative 8 times 2 is negative 16. Negative 8 times 1 is negative 8. Negative 8 times 3 is negative 24. Now let's add down here in row 4. I get 0, 0. 4 minus 16 is negative 12. 5 minus 8 is negative 3. 12 minus 24 is negative 12. Okay? So notice now the first two columns look exactly like we want, so let's keep diagonally down. We want this to be a 1. Well, we can fix that real easy. All we have to do is multiply this row by negative 1. Okay? So I'm going to multiply negative 1 times row 3, and that's my new row 3. Okay? So I'm going to need another sheet of paper here. Let me scoot that on up. Let's recopy row 1. And let's recopy row 2. We're going to multiply this third row by negative 1. 0, 0, 1, negative 1, negative 4. And then we're just going to recopy the fourth row. Okay, now let me slide this on it and let's sort of take a look. I think I'll get this a little more organized if you don't mind. Okay, so I've got 1 and zeros, 1, zeros above below, diagonal down. I've got my 1. Now I'm going to use this 1 to get my zeros up here and down here. Okay, so we're not going to be changing row 3, but we're going to be using row 3. Okay, well let's look at row 3 and look up here at row 1. I need to multiply by what? Negative 3? So negative 3 times row number 3 is going to be added to row number 1. That's going to become my new row number 1. How am I going to change row 2? How am I going to get a 0 here? Multiply by negative 2. Negative 2 times row 3 added to row 2 is going to become my new row 2. And then what about down here? I'll need to multiply by 12, won't I? 12 times row 3 added to row 4 is going to become my new row 4. Okay, So let's put our matrix. Notice we're using row 3. Let's find row 3 right quick and recopy it. 0, 0, 1, negative 1, negative 4. I don't want to accidentally change row 3. Okay, let's multiply negative 3 times row 3 right here and add up here. So negative 3 times those zeros is still 0. Negative 3 times 1 is negative 3. Negative 3 times negative 1 is positive 3. And negative 3 times negative 4 is a positive 12. Let's add those. 1 and 0 is 1. Adding 2 zeros, I get 0. 3 and negative 3 is 0. 0 and 3 is 3. 12 and 2 is 14. Okay, so we've changed row 1. Now, for row 2, we're going to multiply row 3 by negative 2. So negative 2 times 0 is 0. Again, 0. Negative 2. Negative 2 times negative 1 is a positive 2. Negative 2 times negative 8 is negative 4 is a positive 8. Let's add those. Zeros. 1 and 0 is 1. 2 and negative 2 is 0. 1 and 2 is 3. 3 and 8 is 11. And then finally, we're going to change row 4. We're going to take row 3 and multiply by 12. So 12 times my zeros are 0. 12 times 1 is 12. 12 times negative 1 is negative 12. 12 times negative 4 is negative 48. Now let's add. I get 0, 0, 0. This is going to be a negative 15. And let's see, negative 8, 9, 10, that's 60, isn't it? Negative 60. Okay, well, we're getting real close. Let's not give up yet. We've got ones, zeros. Now let's diagonal. We need a 1 right here. So we're going to take negative 1/15 times row 4, and that will become my new row 4. Do you see why we're doing that? Negative 1/15 times negative 15 is a positive 1. We can just use the reciprocal of that number right there. Okay, so let's recopy this. First row, going to recopy. Second row, we're going to copy. Third row, we're going to copy. Now, we're going to multiply this last row by negative 1/15. Notice times these 3 zeros is still zeros there. Negative 1/15 times negative 15 is a positive 1. Now, again, if you need your scratch paper, we're multiplying negative 60, that's over 1, times negative 1/15. Notice we're going to get a positive, and 15 will cancel with 60, won't it? How many times? 4? So I'm going to get a positive 4. Okay. Now the only thing I have left to do is get the zeros above that 1 right there. Let me scoot up and make room. Okay. So using this 1 down here in row 4, to get a 0 up here, I need to multiply by negative 3. So negative 3 times row 4 is going to be added to row 1, and that will be our new row 1. And then same thing here, negative 3 times row 4 is going to be added to row 2, and that will be my new row 2. But notice to change row 3, I just need to add row 4 to row 3 to get my new row 3. Okay, notice we're using row 4 to change the others. Row 4 itself does not change. So let's recopy row 4 down here. Okay, I need to multiply negative 3 times row 4. Well, notice I'm going to get zeros till I get to here. So I've got 3 zeros, then I've got a negative 3, and negative 3 times 4 is a negative 12. So when I add, I get 1, 0, 0, 0. 14 and negative 12 gives me a 2. And then I can use those same numbers. I think I'll just look at them here. 0 and 0 is 0. 1 and 0 is a 1. 0 and 0 is a 0. Negative 3 and 3 is a 0. 11 and a negative 12 is a negative 1. Okay? And then finally, we're just going to add these numbers in row 4 to row 3. So 0 plus 0 is a 0. I get 0 here. 0 and 1 gives me a 1. Adding those, I get a 0. And adding those, I get 0. And we're finally finished with the matrix part. Let's look at the equations. Remember, this was x Y, Z, and W. So my first row, notice says X, no Y, no Z, no W. So just X equals 2. Second row, the only thing I have is 1Y equals negative 1. In the third row, I have 1Z equals 0. And in the last row, I have 1W equals 4. Okay? Now, I think you can see just by looking at this technique, we stay organized, we stay on a certain pattern to go through to find the solutions. It does become tedious when you do this by hand, having to recopy rows and all of that, but don't forget, your computer doesn't mind tedious work, and that's why we've said it's a very nice technique to program and ask a computer to do this problem for you. Because once you set up that initial matrix, then you can just tell the computer, okay, I want to get a 1 up here, tell it how to get it, get zeros underneath. And basically we're getting the zeros by using this type of an operation where we're taking a multiple of one row and adding to another row. And so the computer can do all that nice work for us. Do two other examples for you. These will not take very long. We've covered mainly this sort of technique that you need to go through to solve these systems of equations. But I want to show you something that can happen to you during this process of using Gaussian elimination or Gauss-Jordan elimination. Let's take a look. Solve the following using Gauss-Jordan elimination. And we have this system written right here. What I'm going to do is to write the matrix, and I think since I don't have a 1 in front of any of these x values, I can put these in whatever order I want to. So I think I'm just going to go ahead and put this 2 first. 2x minus 1y, 3z equals 7, and then I'll list this negative 6, 3, negative 9, and negative 1, and then finally the negative 4, negative 2, 6, and 0. Since it doesn't matter what order these equations are in, I'm doing this really for my own convenience here, because I know to get a 1, since I don't have anything here, I'm going to need to multiply by the reciprocal, and I would rather work with halves than sixths or fourths. You see what I'm talking about here? So the first thing I'm going to do is multiply 1/2 times row 1. That will become my new row 1. Let's take a look and see what that matrix looks like if I multiply that first row by 1/2. So 1/2 times 2 is a 1. 1/2 times negative 1 is a